So now let's suppose we know the velocity and its initial position, and we want to find the position at some given time. So according to the fundamental theorem of calculus, we have that s of t is equal to s of 0 plus the integral from 0 to t of vx dx. So this allows us to determine a future position using our fundamental theorem of calculus. So we'll go back to our problem. Let's find the position function s of t, given that our initial position is 0. So according to the last slide, we have that s of t is equal to s of 0 plus the integral from 0 to t of vx dx. So s of 0 is 0. This will be the integral from 0 to t of 3x squared minus 6x plus 4 dx. We've already looked at solving this integral. We got x cubed minus 3x squared plus 4x, in this case going from 0 to t. This gives t cubed minus 3t squared plus 4t, and if we stick in the lower bound we just get a minus 0. So our position function is given by t cubed minus 3t squared plus 4t. So at any given time we can determine the position of the runner. Now suppose we know the acceleration and the initial velocity. We can also find the future velocity. This comes from the exact same formula that we had before. However, instead of velocity being the derivative of position, we use the fact that acceleration is the derivative of velocity. So let's assume we throw a ball straight up with an initial velocity of 4 meters per second from a point 2 meters above the ground. We're going to assume the only force acting upon the ball is gravity. So let's find the velocity. So according to the last slide, we have that v of t is equal to v of 0 plus the integral from 0 to t of ax dx. We know what the initial velocity was. It's 4. As far as acceleration goes, the only force acting upon this is gravity, and gravity is negative 9.8 meters per second squared. We use negative since this is a downward force. So now I have 4 minus 9.8x between the points 0 and t. Sticking in my bounds, I get 4 minus 9.8t plus 9.8 times 0. So my velocity is 4 minus 9.8 t. Now that we know that, let's find the position. So we need our initial starting position, which was 2, plus the integral from 0 to t of our velocity, which we just found, to be 4 minus 9.8. And we want to move back over to x. So if we integrate this, we get 4x minus, we raise 1 on the exponent, and then divide by that number to get 4.9. And then we need to evaluate this between 0 and t. So this gives 2 plus 4t minus 4.9t squared minus 4 times 0 minus 4.9, 0 squared. So our position is given by 2 plus 4t minus 4.9 t squared. And this works beyond just position and acceleration and velocity. If we know some quantity changes at a known rate, q prime, the net change is given by from QB minus QA equal to the integral from a to b of q prime of t dt. And if we know the initial value, we can find the future value the same way we found the future value of position and velocity. Q of t is equal to q of 0 plus the integral from 0 to t of q prime of x dx. So for example, suppose a scientist has a culture of cells with an initial population of 150 cells. Suppose the population increases at a rate given by this function. We want to find p of t. So according to the last slide, p of t is going to equal our initial population, which was 150, plus the integral from 0 to t of p prime of x. So we have 110 e to the minus 0.13, and we switch over to the variable x dx. This then gives 150 plus, if you calculate the integral of this, you get negative 846.15 e to the minus 0.13x, going between 0 and t. So this will be 150 minus 846.15 e to the minus 0.13 t plus 846.15 e to the 0. Anything to the 0 power is 1. So that term just becomes 846.15. When I combine that with my 150, I get 996.15 minus 846.15 e to the minus 0.13 t.